It's a real pleasure to be here with you today and share some of the work that is exciting to me at the intersection of systems and AI. I don't think any community would claim me as their own any longer, but I do have to say Neurexing AI has been by far one of the most welcoming and exciting communities. So thank you so much for having me to chat about these things. What I decided to talk about were kind of three different questions that I hope will give you a sense of what I find really exciting at this intersection of systems and foundation models. The first thing I want to talk about is how did foundation models change the systems that we build? And I'm going to ground this in an application that I was working on for almost a decade, and that foundation model is kind of radically changed. And I think there's a general principle here that I'll try to extract for you, which I call these kind of death by 1,000 cuts problems. These are problems in which every individual task is actually relatively easy, but the sheer breadth and variety of tasks that you have to solve to complete the problem are really challenging. And so I'll show it in this one application that I care about, but then hopefully you can see it in a couple of others. The bulk of the talk will be about efficiency. I like to make things run fast. But in particular, what I'm going to try and share with you is how we ground some of these things in very classical ideas. I learned these ideas from the data management community, but there's a ton of these different ideas and systems and various different areas. What I'll talk about is the key ideas behind something called flash attention. Now, if I do my job right, you're going to think, oh my God, that's so simple. I can apply these principles anywhere. If I do my job wrong, we'll probably just forget about it, right? The next piece is, I want to talk about these new class of models which are based on signal processing. In particular, one that's exciting to us is this model called S4. And again here, I'm going to try and give you a sense of what I think are kind of the interesting ideas that have emerged in this class of models. And they're basically models that have to deal with really long sequences. So they're very efficient kind of by construction. And we'll try and understand where their strengths and weaknesses are, because I think these are pretty exciting. Now, I will warn you, there are some integrals in there. I know most people are hungover, so apologies in advance. These are just like, high school integrals, don't worry. All right, so the last piece, the first thing I wanted to say here was this: how do I learn to love foundation models? And I have to say, I absolutely fell in love with these technologies. They just really changed a lot of what we were building in a really exciting way. But first, let me set the scene on foundation models for a couple slides, then I'll tell you about the problems that really convinced me, hey, these things are pretty big. So this is an old idea of foundation models. They've been popularized by ChatGPT, but at their core, this autoregressive language modeling idea is something that we've seen for a long time. We have a large corpus of text, you try to predict the next word, so the mouse ate the blank, cheese is more likely than house, and you have this kind of empirical probability distribution of text that you've gotten from some web source or code or wherever it is. Natural language models, what we've tried to do is represent that probability distribution compactly with a neural net. We hope that neural net generalizes in interesting ways, but that's kind of its core thing that it does. This also gives us a way to generate, which is now very familiar to all of us who use ChatGPT. And also, why I got so fascinated originally was I was working on weak supervision. This turns basically every sentence that you see into a training example, which is really exciting to be able to train these large models. Now, as I mentioned, ChatGPT and OpenAI deserve a huge amount of credit for popularizing these models. These foundation models started out as autoregressive neural language models. They've since grown to images and video and audio and more stuff coming. They're huge, they have a large number of parameters. But what was exciting to me was this kind of emergent behavior that I could just express my task in text, and then all of a sudden I would get a solution. So get capital from country, I give it a couple of examples which are few shot, I ask it for another capital, and often GPT-3 would get the right result. This is pretty mind-blowing to me when it happened. It was really exciting. We've been trying to build things that look like this for almost a decade. So it didn't just do that, it translated languages, it did little bits of Q&A, and it was kind of worryingly bad on arithmetic, but a lot of people have worked on that since then. Now, I was working on these data problems, and I want to share them with you because they have this very specific concrete feel, this death by 1,000 cuts feel. That's where every problem is easy, but the breadth and variety is hard. And foundation models really just blew a lot of this stuff out of the water. So this is the work of three folks: Ivanica, who's one of my PhD students, Inez, who was my PhD student, oddly did her dissertation in non-Euclidean geometry, and then started a company called NumberStation in this area, or who now works at NumberStation as my postdoc. So data cleaning is this problem that we're thinking about, and I kind of glibly call it data plumbing, which is I have a bunch of data sources and I've merged them together. And this may seem like a really small bore problem, but trust me, it's really hard. So what you're seeing here is the same address, place, this bar, represented in different ways in this data set, but there are errors. For example, in the US, if you have an address, it has a unique zip code. You see there are 2 zip codes listed here. One of them is incorrect. You'd like to fix that up. You see that there's a typo. Someone's entered Chicago without an H. You'd like to be able to fix that up. Johnny O's doesn't obey the data distribution. My point is, if you look at this, you're like, oh, I could write a classifier that fixed many of those, or maybe even a Python program. But the sheer variety and breadth of knowledge that you need to fix this at large scale, that's what's daunting about this problem. So you may look at this, and I know a lot of my friends in AI, when they look at this problem, they're like, oh, that's kind of like the stuff we do that we're embarrassed about before we start doing any, the real work. I would just say there's another community of folks that this is the problem that they care about. And the reason they care about it so much is this is a $1 trillion problem, apparently. So these two jokers who are friends wrote this wonderful book on data cleaning, Ehab and Shu, and they talk about how this is, at least in the US, a huge problem in terms of the data quality and the data cleaning things that go underneath the covers. And I was peripherally working on this problem. I had done some work both in industry and in research on it. And I would say I was really unclear that this would be solved in any meaningful way because it felt like there was just this long tail of problems. We could make it better, but could we really make a big leap? Now, when I talk about how it's difficult to actually write down all the information that you need, that breadth of problems, I'm speaking from experience here. These folks came and visited the lab, Theo's a postdoc, and we tried to basically write down all of the rules that were happening in a lot of these major industrial data sets, compile them with stuff that we were doing in like 2017, embeddings and kind of the learning stuff underneath the covers, and then we would output a clean table. And the point was, this was actually a jump in the state of the art at the time in 2017, and it got commercialized, and 2 of those characters now work at Apple as a result of the acquisition, and they really tried to do this. With Ehab in particular was a serial entrepreneur. This was like, a pretty interesting set of tasks. All right, so how do foundation models come into the picture? It's about 18 months ago, I was asked by Sigmod, which is a community of people who worry about the management of data, to come give a keynote. And I thought before I would do that, I would revisit some of these results and try and understand how foundation models actually change some of that problem. So I asked Ivanica, who was a first-year PhD student at the time, to just run GPT-3. I want to point out that most people in the audience 15 months ago had not ever run GPT-3, which I was kind of surprised about, but it was kind of more broadly held than you might think. So what she did was extremely simple. Run every tuple through the database and ask, is there an error in this field? And try and correct it. Very, very simple problem. The zero-shot behavior of this works. And by the way, that's a miracle, right? Like the fact that this was never trained for this task and we have this kind of transfer, this is like a pretty impressive result for machine learning. But as you see, it's not really close to the state of the art on a lot of these tasks. But with just a few examples, I think it was 32 in the original one, all of a sudden it was surpassing the state of the art. And to me, this was absolutely wild. Few shot, not trained for this, and for a very economically important field, all of a sudden it provided a new tool. Not that it solved it, but it provided this new tool. That was really shocking to me. Now you may look at this and say, those OpenAI people are geniuses, they're doing all kinds of things, we don't know what they were doing, maybe they trained it to be a data cleaning agent. And I often say, Ilya deserves the Turing Award. I mean, I think the contributions there are amazing. Maybe not Employee of the Month, but certainly the Turing Award. Now, sorry about that, I couldn't help myself. Anyway, so in particular, we at the time ran another large model, AI21 Labs model, and we looked across how it did on these performances. Pretty similar. And Meta deserves a ton of credit for stepping up over the last couple of years and building those wonderful open source models, which are 2 to 6x smaller than GPT-3, but for this economically important problem, they've closed the gap. And why that's interesting to me is, I think we underestimate how much economic value is still left in these models to be exploited as kind of systems over the next couple of years to make our society hopefully better and cheaper and freer and better educated and better healthcare. There's a ton of value locked already in these models that we haven't done anything with. So that's why I'm so excited. As a systems person, I'm really excited because it's a new paradigm. The old way of doing computer science was narrow down your task until you knew exactly what you were after. We would tell you to get as precise as you could in your specification. And once you were precise, then you could train your classifier, you could debug your data, and that's how you build machine learning systems. I would preach this to my graduate students. And in some ways, I couldn't have been more wrong, at least in terms of foundation models. Foundation models instead said, solve a very general, broad problem. Put all that junk knowledge, all those zip codes, all those misspellings, all those data distributions in a huge foundation, and then go use that to attack your problem, and attack a breadth of a problem. It's So it's this depth versus breadth trade-off that I found really exciting to study. I don't know which problems are depth first and which problems are breadth first, but I'm really excited to study them. All right, so I wanted to tell you about these data plumbing applications, this death by 1,000 cuts feel, thousands of sub-problems, each are easy, but the breadth is hard. I also wanted to point out, because I love the open source, that the open source caught up quite quickly, which is really exciting for these models. Now maybe you're IR researchers, you don't care at all about data cleaning. That's cool, I understand. But you probably care about robots because they're awesome. I don't know anything about robots. I just like them. I like that little robot that was walking around in the exhibition hall yesterday. I thought it was really cute. I took pictures, sent it to my kids. I go to all these talks. When I would go to robotics talks though, it had a similar vibe. What I mean is they would tell me what they were doing to solve their task for their model, and it felt like each of those individual tasks actually was fairly easy. But the breadth and variety of those problems, that's what really stunned me. And so I've been really following this field, hoping that foundation models make an inroad, and I think this kind of OpenX embodiment set that people put out was kind of a step in that direction. So I'm hopeful that there's a more general principle that these death by 1,000 cuts problems aren't limited to data cleaning and data operations, but really could be broad for more systems-oriented fields. So I don't know anything about robotics, but I think they're awesome. All right, so to build new applications, we probably need more capable FMs. We don't just need text FMs, we need things that can look at images and video and all the rest. And so efficiency is gonna be kind of core on our mind. We've gotten used to this, but this is shocking. Like, I remember when the Elmo paper came out, and I thought it was mind-blowing and large and crazy, and was implementing it, and it was really exciting. It was in 2018. Look at that curve. It's stunning how quickly these things have grown. It's a log scale, the orders of magnitude. Now, one of the things in systems that I've always liked about machine learning and why I wanted to work on it is quality and efficiency are really intimately intertwined. If you make things get bigger and faster, that's been a pretty good recipe to get them to higher quality. It's not the only thing, maybe not even the most interesting thing, but it's certainly been a thing that's helped over the last while. So it's not just efficiency we're going to care about. There's also efficiency along certain axes of these models. So in 2019, I became super interested in, because of these prompting and other things that were going on, how is it the case that we can put more information into the model? And so we started thinking about why we wanted to have longer and longer contexts. And so you'll see this theme lurking through the rest of the talk. How can we build systems that can get longer and longer sequence lengths? What I'm showing here is that quite recently, many of the commercial models are actually starting to go through that trajectory and add in not just scaling to get larger, but scaling to get more information in them. And we'll talk a little bit about that and why I care so much about these models that scale well into sequence length, which in 2019 was admittedly like a mathematical curiosity. All right, so how can we make these models more efficient? So I want to tell you two things about the state-of-the-art of accelerators right now that are fundamental. I'll talk about NVIDIA GPUs because they're by far the most dominant, but basically every accelerator kind of looks like this to a first approximation. And I think these trends are fundamental, so you may want to be aware of them, even if you don't work making fast code day to day. The first thing is, NVIDIA markets these things that they call tensor cores. Basically what a tensor core does is instead of multiplying two floating point numbers, it multiplies two 16 by 16 matrices, roughly. Now, you may look at that and think it's an oddity, but the penalty for not using the tensor cores, or the benefit of using them, is staggering. It's on the H100s, it's a factor of 16 of using the tensor core to multiply matrices versus using the regular kind of hardware that's there. And this is really fundamental. And the reason it's so fundamental is, what we can do in hardware is, when things are local, we can make them really fast. And that locality is king. So these kind of tile-based algorithms, they're going to be around for a while. And basically every accelerator has something that looks like this inside of it. The other thing that's fundamental is the memory hierarchy. Now, back when I used to teach databases almost 10 years ago, we would worry about a memory hierarchy where the slow stuff was disk and the fast stuff was DRAM. It was only even 7 years ago we would talk about that. Now, we have a memory hierarchy where the small, fast memory is the registers and the shared memory on disk, and the slow memory is what's called HBM. This is the memory that's actually on the GPU. When they sell you a GPU and they say it has 40 gigabytes, they mean 40 gigabytes of HBM, not shared. That's right. Now, why this matters is, as we'll talk about, what database people worried about was not the compute cost so much, the flops. They worried about how often they touched memory, and I'll come back to that in a second. And so they worry about the IOs, and for our case, it's going to be how often we read and write from HBM. So the reason is there's always this classical balance. As you make the systems faster and faster so they can do more operations, eventually your bottleneck is how fast you can feed them with data, with information. So the memory bottleneck is the thing that basically comes out. And so database people lived in this world when disks were spinning and they were very, very slow, but they could do lots of computation on every piece of data they pulled in. So I'm just arguing that it's a natural place to look for ideas. Even though you may think, it's inside the GPU, it's really fast, the HBM is dramatically slower than the rest of it. All right, so we're going to worry about attention. Okay, so this is a wonderful, that's a standard attention diagram. It comes in, you mix the sequence, then you mix the dimension. What I'm illustrating here is a causal variant of attention. Basically every output, so the input here is a matrix, that's an n by d. The output is an n by d matrix. And every particular output value depends on, in this case, all the preceding values. It's some mixture. In the preceding slides, I'm talking about this non-causal, causal version, but what I'm going to talk about next is the causal version. Everything applies almost exactly, it's just easier to talk about. You'll notice here that in the sequence length, as I talked about in the previous slides, as you scale the sequence length, it's growing, the runtime is growing quadratically. You're paying attention to all n preceding positions, and so as a result, you just have this quadratic runtime. We'll come back to that. All right, so how does attention work? The first thing you do is you create these very famous matrices, the queries, the keys, and the values, Q, K, and V. I've illustrated them here graphically. What you then do to compute O is you take Q and K's outer product, and you compute a softmax. What I'm illustrating is that one output of the second output, for example, depends on only the second query, but depends on seeing all of the different keys. It's a softmax over all of the different keys. That normalization I'm emphasizing, because we'll come back to that when we talk about why we want to make flash attention fast, or how to do it. So the way this works is you compute the attention scores with an exponential, you then weight the vectors, you compute that normalization, and then you compute the output. And I would just say the standard way to execute this is what we call kernel by kernel, which is you launch a kernel every time. So every one of those intermediates goes back and forth to HBM. So for example, the A matrix, which is quadratically sized, traditionally would have caused quadratically many writes to memory because you blew it up. So that normalization I called out, so I want to come back to it a little bit later. All right, so what is flash attention's main idea? If I do my job well in these next couple of slides, it'll be so simple. You're like, oh, that's obvious. How come we didn't do that earlier? Yeah, I don't know. So the first two ideas are really simple. We want to minimize I/O. Okay? To minimize I/O, we're not going to worry about flops. Actually, we'll do more floating point operations in the end, but we don't care about that. To minimize I/O, the second thing that we're going to have to do is we're going to have to do aggressive fusion. So fusion means when I bring in a piece of information, I try and run as many operations on that as I can. Traditionally, fusion is done by graduate students or professors if the graduate students don't want to do it. In the future, relatively soon, you'll have these wonderful compilers. PyTorch is building one, Modular's building one, to try and do this more automatically for these workloads. These are incredibly classical ideas. I learned them from databases, but you can learn them from wherever you like, high-performance computing. This thing actually works. So what I'm telling you is really, really simple, but it actually worked. It was a jump on the state of the art, okay? Even though it's incredibly simple. All right. So the first idea you need to know is what we call, database people would call a nested loop join. The idea here is what you're going to do is you start on one block of Q and you go through all the blocks of K. So the question is, how many IOs do I do? Well, I have to read all of Q and I have to write the output. Nothing I can do about that. But every block of Q that I read, I have to go over both K and D. Okay. Now, the database idea is super simple. What I'll do is rather than look at one block at a time, I'll read 3 blocks at a time. I don't change all the floating point operations that I'm doing, just the block size. But because I've now taken, instead of reading 9 chunks of Q, I'm only reading 3, I've actually changed the I/O cost by a factor of 3. I've reduced it by a factor of 3, basically doing nothing to the operation. Now to do that, I need to be able to operate kind of tile at a time as I run through this algorithm. So I'm going to show you how we do that. But this is it, that's all blocking is. I should say, in flash attention, we use 8x8 kind of blocks, and that's where we're going to get a lot of speed. The second piece is that normalization is going to come back and bite us, but it looks just like a running sum. So let me show you what I mean. We'll run into the problem. So here's what happens. I load my Q, my K, and my V into memory. Then I compute those attention scores. I compute the normalization. And then I compute the first part of the output. Right? I haven't seen all the vectors and the Ks yet, so I can only compute the first part. So far, so good. And then I free the things from the input. This should worry you though. The normalization for that output is almost certainly wrong. And the reason it's wrong is is I highlighted here in red, you haven't seen the rest of K and V, you haven't seen the rest of the softmax. So we haven't normalized them correctly. We're gonna have to fix that up, just like you fix up a running sum. So I load my K2 and my V2. I again compute the attention scores locally. Now I compute the normalization up to the second position, compute its output. So far so good. But I take the old output, which now has a denominator of Z1, which is the old partition function or normalization, and I just multiply Z2 by Z1 in the way I've shown here, and now all of them are normalized correctly, and I add them together. And the point is, all I had to do was keep the normalization, to do that normalization is as a running sum, keep the normalization constant, the Z's, and the last O that I was looking at. And I basically have to do no other IO. I can just stream over K and V. So I minimize the IO by blocking. That's the first thing. And the second thing is to do this fusion, we're basically doing an aggregation like a running sum. I learned this technique from Jim Gray, who's a personal hero of mine. He's the reason I got into databases. He wrote this wonderful paper in 2007 about all the different aggregates and which ones were algebraic and which properties they needed. This is something that's just as classical as can be. And it's just this very classical algorithm that you would get, say, in week 3 of a database course. My point here isn't this such an amazing thing? My point here is there's a whole canon of systems in AI that we really just haven't explored yet, and I'm super excited for what's going to happen over the next couple of weeks and months. All right, so it was a big speed up. It was pretty cool. We're excited about it. Used a lot less memory. This is all awesome. Great work. One thing I can't help but brag about is Tree. Tree I adore, and one of the things I love is, in my lab I always say to my students, show, don't tell. And Tree did this to an incredibly high degree. Tree went and basically competed in MLPerf by himself. And this is a quote from that article when it came out. And for a time, he was actually winning MLPerf. I'll say all the winners now use flash attention, which is wonderful. But he actually went by himself and put this together. And that just deserves, that takes a lot of guts. And it was just really exciting. The other part about it, which I'm very worried that we might lose over the next couple of years, so I bring it up, is AI has been a wonderful and welcoming community. One of the reasons I first got into AI way back, machine learning, whatever you want to call it, even in the hog wild days, was I'd put some code online and someone would use it right away, and they would start to integrate it into their workflow. That open source vibe is amazing. The people at PyTorch were unbelievably helpful in getting these kernels adopted. Hugging Face has been amazing here. Meta, Jax, Microsoft, NVIDIA. We have a really dynamic community, but we could lose it if we're not careful. It's really exciting. Okay. All right, so the next part of this talk is about can we remove attention? And often when I talk about this work, people are like, do you dislike attention? No, I love attention. I just spent the last 15 minutes telling you how to optimize it. It's a wonderful thing. I'm just a curious person. Do we really need it? I don't know. Maybe not. So we'll find out in the next couple of slides kind of what we've learned about this. I will call out another amazing person in the community, Sasha Rush. If you're not following Sasha, you absolutely should. He gave a much better version of what I'm going to talk about, Do We Need Attention, at SysML this year. And his writing and his code, I end up following and bumping into him on GitHub's various places. He's amazing. He's one of the people we're really lucky to have in this community. It's an awesome place. Please keep it amazing. All right, so as I mentioned, our motivation for getting rid of attention, potentially, is long sequences. That's the practical motivation. I'll come back to my real motivation in one slide. Practically, some data comes as long sequences. Data, audio, DNA is billions of base pairs. We can also cram in tons of few-shot examples, which seems pretty cool. When we started this project, really the standard models couldn't have it. GPT-1 had only a 512 context length, and as I mentioned, transformers are scaling quadratically in their sequence length. So we kind of took two parallel paths to this. One is better hardware algorithms. So we tried with flash attention, and now people have followed up to make that path really fast. Just optimize the crap out of it on hardware, and there's a lot of juice to squeeze there. The other approach, which I'll talk about now, are new models. Now, as I mentioned, I actually wasn't totally motivated by that, or honestly, that wasn't my total motivation. I was really motivated by this inductive bias issue. So the idea here is you give me this image, and I flatten it into one single pixel. And then I ask you, is it a car or a boat? Some CFAR like that. Sequential CFAR, if you know the tags. And this is really interesting to me because when a human would do this, this would be hopeless. If you gave me a picture and gave me a one pixel vector as a flat thing, I would have no chance of classifying it. Machines could do something, but there was a huge gap. And I wanted to understand, why is there this inductive bias underneath the covers? Do you really need this spatial inductive bias for the machines to reason? Do they have to reason like us, human beings? So I was fascinated about it. All right. So there's another benchmark that came out that was really exciting from the Google folks, which was about how to benchmark efficient attention. It's called Long Range Arena. It's extremely cool. We found them basically because we were playing around with the sequential CFAR things. They had a much greater library of places where they were seeing possibilities to improve attention. This was the leaderboard in 2021 of this attention, and they were basically looking at a bunch of very cool linear attention variants, some of which we still play with. I want to draw your attention to two columns on this thing. The first is image. That is that sequential CFAR task I was just talking about. It's a really interesting task. You've probably trained CFAR to 90s or high 80s on your laptop or on a small GPU, and you see the sequential version is lagging quite a bit behind. The other column is this thing PathX, which were these large images where you had two dots, and you're trying to say are the two dots connected. And the reason there are X's is that every model was basically random guessing it. So there are three approaches that we were trying to improve long sequences. Improve the hardware, the utilization on hardware, approximate attention, and this last one, which I'm going to talk about most, which is using RNN-based kinds of ideas and signal processing ideas. All of them are great, I just happen to pick the last one. All right. So the idea is we're going to replace just the signal processing box, the signal mixing box, with this new operator, S4, that's based on signal processing ideas. So this was inspired by Albert and Karan. Albert's now a professor at CMU. Karan's now running this company, Cartesia, which is a small company just started. And basically S4 is a classic state space model. So if you're an EE person, you've seen these in your undergrad right away. It's an LTI system. But we're going to tweak it for deep learning. The first thing we're going to get, as I'll show you pretty mathematically and nicely, is that signal processing people are obsessed with stability. They understand bounded input, bounded output stability like nobody's business. It's simple and it's clean. We can use it right away. This is a challenge when training these models. A second thing which was quite surprising is, I've always thought about CNNs and RNNs as quite distinct models. But what I'm going to show you mathematically is, these models actually unify both. Now these are CNNs in a kind of different way than we're used to. They're convolutions where the filters are potentially as long as the input. But we're going to be able to view the exact same weights and operate on them either as an RNN or a CNN, which is quite exciting. And the last piece, of course, is that we're going to make this quite fast. These are going to be asymptotically more efficient than transformers. We're eventually going to be able to process sequence in n log n time, which is then a challenge to make practical, and I'll share some results there. Now this thing is extremely simple. Very simple signal processing ideas, but I just want to point out it had a large improvement on LRA that surprised me. So here's that improvement on LRA. This is the first of its kind to solve PathX. It was like a 26-point jump on this benchmark that a bunch of folks had played at. I also want to point out that the image task, that spatial bias seems to matter less than I thought. And that was really the thing that was interesting to me. And since then, many people have followed on and pushed these numbers up higher. But I just think that's really interesting. I don't know what to do with the observation, but I really like it. Okay, so what is signal processing? Well, signal processing people view a signal of d dimensions at n time steps as input, and an output is a signal of d dimension at n time steps. It looks a lot like our X and O matrix that we had in attention. They also think causally. They think that time moves left to right through this, and things like GPT are also kind of causal. So far, what I want to emphasize is, we've really done nothing. It's just symbol pushing that we've been able to move into this model. So what does signal processing actually buy us? Two big ideas. The first is, over 100 years, they figured out a bunch of models which are relatively simple, but capture pretty interesting phenomena. These aren't the best models you could ever use, these LTI systems, but they're a simple and very well understood starting point. So I argue it makes sense to start there. The second piece, which I think a lot of machine learners don't necessarily love, is that they have this idea that a signal is a continuous object that then is discretely sampled. And that idea allows us to do a bunch of stuff. In particular, it allows us to use all our discrete tricks, which are more common in machine learning and AI, but also a bunch of 20th century mathematics that knows how to do integrals and solves things exactly. And I'll show you at least one of those tricks in the next couple of slides. I think it's an incredibly powerful idea, and it was really helpful for us to think about. And as I said, it's going to teach us about stability in a trivial way. We're going to use theorems from the 1800s to be able to prove that our models are stable, which I just think is awesome. All right, so what's an LTI system? If you've never played with one, this is what's called a single input, single output system. You have some curve that's coming in, which is typically called UT, that's the input, and some output curve YT. You have some hidden state, which is much higher dimension usually than the input and the output. We'll take the hidden state as large as the input when it's discretized. It's going to be a huge thing. Okay? Now, I haven't told you how that hidden state evolves yet, but it's going to be constrained. And the LTI people say there's lots of things that can fit into basically letting it evolve according to an ODE. Okay, so I'm going to show you that in just 1 second. So here's what you need for the ODE. You need two matrices A and B, and we're going to learn those matrices. And basically it says that the hidden state can only evolve according to this equation. It basically says the change in the hidden state is proportional to some learned function of the input plus the previous state. The output is then from projection from this linear projection from this high dimensional state down to 1D. This is all that an LTI system is. Okay? I'm just saying it's something that's surprisingly powerful and well understood. This is not the best model. If you're a signal processing person, you say, oh, you should use X, Y, or Z. You're probably right. But we want to start with something really, really simple that we can understand all right, so it turns out that one of the beautiful things is because it has this continuous object lurking in the background, you can use high school calculus. And in particular, you can get out this nice expression. And what this says is the hidden state is exactly this function, x of s, in this convolutional style interval. Okay? This is exactly what it is. This is wonderful. Just solve the ODE. Then when we realize it, we have to discretize. We'll come back to that in a second. So the immediate win is, well, this can tell us exactly when the system is stable. Basically, as long as the eigenvalues are in the left-hand part of the plane, which every EE person memorizes, and the reason left-hand part of the complex plane matters is E to those values goes inside the unit disk, you know that this thing is not going to blow up. The system is going to have bounded input, bounded output stability, which is really exciting. Okay? So when we train, we can fix our A's or representations so that the eigenvalues satisfy this problem. And that's going to be one of the arguments. Now to implement this on a machine, we can't use continuous objects. We have to use them as discrete. And integrals are just big, smooth sums, basically. They're actually nicer to deal with than functions. And so what we'll do is we'll break that sum down into functions. And what happens in signal processing is you think that you're going to sample at some regular frequency t, and then what I'm denoting here is x bracket k means the kth sample, which is at the point kt. Okay? So you're seeing this animation that the integral is just this nice, smooth sum. Right? Cool. All right, so now that we're in discrete land, we can relate it to more familiar machine learning concepts. The first thing is, you can view this as a recurrence, as an RNN. So I'll introduce notation G here, which is basically the B times the input. It's all the modifications on the input that we had. And with just a little bit of arithmetic, I can move it out so that I get x of n plus 1, the next hidden state, is t times gn plus some term that's kind of downweighted. And I'm illustrating the downweighting here in the visualization. RNNs are super fast, so if we did manage to learn the weights, the B's, the A's, all the rest of these things in the filter, then we could run this as an RNN automatically from the same parameter stations. Super cool. With just a little bit more notation, I can take that E term, the exponential there, and put that matrix exponential into this function f. And that becomes a convolution that's probably more familiar to most people, which is a discrete convolution. But notice this discrete convolution is of length n. It's a huge, long convolution. It's not a 3x3 convolution like a ResNet. It's actually as long potentially as the filter. So that's going to be challenging to process, but this model says they're basically both the same. So the key technical challenge is to make these SSMs fast. Those long comms are hard. If you think about it, that F, that filter, is huge. And so if you materialize it at every time step, you'd be toast. It turns out that you don't ever have to materialize the hidden state. That's a really important observation. That allows you to go fast and allows you to have runtime that's proportional to the input and the output, not the massive hidden state. The hidden state is important for representation. It's actually not important for implementation. You can check out the blog. The blog has more details about exactly how that works. The second thing, which we spent a lot of time on, and Albert did a bunch of really brilliant things, inspired the Legendre memory by Legendre memory units, is how do we make that A have that nice eigenvalue structure so that we know it's stable? Things like diagonal matrices are really easy to keep this structure because they're scalars on the diagonal, you can keep it. But computing matrix exponentials in general for expressive classes is actually pretty challenging. So we had to do a ton of work to get that to happen over the last couple of years. And the last bit is this practical fast convolution that we needed. Now, I love this slide because DALL-E 3 made most of the art in this talk, or all of the art in this talk, and it made this poster. I didn't give it the tagline. I still think it's hysterical. Too fast, too furious, revving up the equations. I have no idea what that means, but I love it. It's supposed to be Fourier, by the way. That's the thing. In any case, the thing is we had to do the same type of operation that we did in flash attention, but now on FFTs and convolutions. If you naively run FFTs, you have terrible memory behavior. If you can somehow group them together in nice ways and be IO aware, you can get back to that kind of nice utilization. Flash attention, if you recall, was about 72% utilization. Dan and Herman got to 65% utilization. I would also say that Dan's on the faculty market this year and Herman's on the PhD market, and you'd be smart to hire them. They're amazing. So the point is there's not really a hardware trade-off after you do a bunch of work. It's really algorithmic. This thing is going to do a lot fewer operations. And this led to what some folks have called, Sasha called, an RNN renaissance. And I want to say it's been super fun. I have to say the last year and a half or 2 years of research I've absolutely loved, because you've had a ton of people contributing amazing ideas like S5 and Mega and RWKV on super technical topics that were really exciting for us to do. And there's just been so many more that I can't put on here, and they've been pushing the state beyond. So now you listen to my talk and you're like, should we use these models everywhere? And maybe I'm a California optimist, so I sound happy. I know it's irritating, but I'm happy about everything, so I am. So you're like, maybe we should use these things. I say, well, maybe. But there's actually a pretty big gap on language. So it was wonderful on LRA and the signal processing tasks, but when we actually deployed it on language, there was a gap. Now, the standard way you measure a language model is complexity. This is the score of how predictable the language is. To give you a sense of this measure, S4 was 5 points worse on perplexity versus transformers. And that's a staggering number, because 5 points is about the difference between a 125 million parameter model and a 7 billion parameter model. It was a big gap. So you started to wonder, why is that? So we went back to work that other folks had done, which was amazing. This associative recall task. So the task here is I give you letters and numbers. The last letter is a query, in this case C, and you have to tell me which number is associated with that letter. It's a lookup task. Attention can crush this, because it's a very easy lookup task. These two variants of S4 that came out later that are supposed to be better on language were better, but there was a gap here too. And so without going into too much detail on this piece, Michael Polly came along and did this thing Hyena, and he showed he could get 100% on this underlying operator, and did it in a very exciting way while still maintaining speed and all the rest. So this is what the picture looked like as of a couple of months ago, or a couple of weeks ago, I guess, 2 weeks ago. We had S4, which was a bit worse, but then in quick succession, people were coming down to this very strong attention baseline. All the baselines are released. Eleuther made a wonderful harness. These are all at 350 million. You can start to play with these things. RWKV has been releasing even bigger models. And so there was this baseline here. These are closing the gap without attention. Part of the reason I love academia is you can worry about tiny problems. It's like, well, it seems like a small problem, but why is it worse? So we kept asking, we kept poking at it, and Simran and Sabri came in, and they actually came up with this idea. It took us a surprising amount of time. There's just a small twist. The small twist is what a transformer can do is not one lookup, but many lookups. So what MQAR is multi-queries. We don't just look up one letter, we look up many letters. Now we can worry about scaling in the letters, the vocab size, the model dimension. And what we found is that all of these models can, quote, solve the task, but how they do it, their scaling is quite different. And this relates to a bunch of things in parallel circuit complexity that I won't get to, but this is a really interesting thing where we can start to study the scaling. And so what they realized is that attention can solve these things with a small number of dimensions, roughly logarithmic. Whereas Hyena and RWKV require, and all the convolutional models as a result of their reduction, require model dimensions that scale with the sequence length. And so you get charts that look like this. They'll solve it, but they need more capacity to do so. So when we started looking at these MQAR things in the wild, we started thinking, well, okay, MQAR is a nice synthetic, but does it translate? This was really insightful. Simran and Sabri did this. They said, we're going to take the pile and we're going to segment out which ones are AR-like, which sentences are AR-like. So these are things that have repeated bigrams. Common buzzard is repeated twice. There's kind of an implicit lookup the second time you're doing the common buzzard task. That's about 7% of the pile. The non-AR slice was basically everything else. What they found is that the attention gap, 82% of it was explained, even though this is a pretty rough proxy for the task, by just what's going on here. And this made us think, maybe if we solve this task, we can even close it. But the other observation was, actually these convolutional models are slightly better on the non-lookup task. So maybe there's hope to go beyond that. And so we started this kind of architecture, and I want to give another shout out here to a paper I love. I love the T5 paper, I'm sure many of you do too. I love the vibe of it where it's like, hey, we just want to say what are the common elements that are going on. If you're outside this little tiny sub-community, all the papers look very, very different. But if you're inside, I would say there's a couple of really common themes. Simran and Sabri tried to boil them down so that more folks can participate and come into the field in a more easy way. The themes are long convolutions that are scaling with the input, not necessarily the full input size. Gating is a wonderful idea. That's multiplying in this kind of component-wise way of the sequence. That's an old idea. And data dependence. And Mamba just came out from Albert and Tree, which did this and still kept that subquadratic runtime. Based is basically just simplifying all of the things that people are doing and trying to get to something nice. We don't have T5 level niceness left, but we are inspired by that. One thing I want to point out is that this new convolutional architecture does scale for MQAR a little bit like attention. So it has the same kind of dimension scaling that the others have, which is interesting. So the point is very recently, this is in the last week run up to NeurIPS, both Mamba and Base, and I'm sure 5 others will come out in the next couple of weeks, are now attention free and actually getting you lower PPL at 350. Doesn't mean they're going to get you lower PPL necessarily at 100 billion, but it's interesting to say there doesn't seem to be any fundamental kind of block, and that's to me extremely exciting. I did want to point out a little bit that there is another bottleneck that's lurking for truly subquadratic models. We talked a lot about the signal processing part, but there's also this MLPs, and I've become obsessed with them. There's a whole line of work, check out Dan Fu's talk, about trying to understand what's going on with the MLPs and can we slim those down. They become a bottleneck at much larger dimension sizes. So the questions that were driving our work really were threefold. I shared with you, I hope, a little bit about how foundation models change the systems that we're building. I also talked a lot about how classical ideas from signal processing and databases were interesting bits of canon to bring into the field so that maybe we can make these models more efficient. What I thought I would end with is just why I think there's such a bright future in AI for 2 minutes in systems. The first thing is, we weren't using these models really 15 to 18 months ago in the way we're using them now. We knew intuitively that you train them once and use them multiple times, but it's not really clear we were doing them. We were kind of just showing them to each other, if we're honest. Now, people are using them on like a daily basis, and inference has become an unbelievable task. I would say even the last 3 or 4 months, the speed of inference, if you watch on a bunch of the commercial servers, are just going through the roof as new ideas come in. Of course, people were thinking about this. MQA and GQA a while ago. Speculative decoding was an amazing paper. VLM was really exciting. Flash decode, Mapformer. There's a ton of exciting work here. My point is, this really kicked off like 6 months ago. Wild to think about, but that's the whole thing. Another bit is, there's a big difference between low latency systems and high throughput systems. When you don't care if it returns in a couple of milliseconds, but you want to say run on 100 different documents, or 1 million different documents. We're just at the outset of seeing that system's pitch as people are actually using these foundation models on all the back of house data cleaning edge tasks that I think are going to happen in the next one. There's new data types. I do want to call out that there's all kinds of things you can worry about from Kunle about how to program these systems, what the right accelerators and hardware that's just happening, what are the right systems to build that are systems of record underneath the covers. There's tons of stuff. But I wanted to use my last 2 minutes really on just something simple, just to thank some folks. So these slides were really built in large part by Simran, Sabri, and Dan, and Dolly 3. That is how Dolly 3 said it wanted to be represented. I didn't have a photo. And the 3 of them, I would say Dan's on the market, Simran and Sabri will be on the market soon, and they're just absolutely amazing. And the number one thing about academia is students, so be nice to your students if you're a professor. Second thing is I want to thank all the folks. Those are mostly students who have been through the lab who made the place great. I also want to thank the UB folks who were on a bunch of these papers and have been wonderful collaborators. Actually, Audrey since grad school, a bunch of the Stanford faculty, and also Ben Recht, who I'm sure didn't want to be thanked, but I put him on there just to troll him. The last thing I would say in kind of concluding thoughts is foundation models are in their infancy. We don't really use them yet to a first approximation. That's going to have an unbelievable impact on the economy and science if we're right. If these things are big as we hope they are, there's a ton of ways that they're going to be deployed. And that's going to create new algorithms, new opportunities to use them, running them on mobile, running them on the edge, running them on tiny little devices. They make engineering easier. They're like the Python to the C++ of the last age of machine learning. They're really wild about how they change how you build these systems and how quickly you can build them. When I mentioned Ivanica did that before my keynote, she did it over a weekend. That would have taken person decades of PhDs in the previous approaches. I'm just astonished by it. All the things I mentioned, I covered a lot of terrain. I tried to put this and some of the course material for AI and systems online in this GitHub. My students put it up there. Please feel free to leave comments and things. I hope to build more of a community as people get excited about this and to just provide resources of the stuff we're up to. Thank you so much for your time and attention. It was wonderful to spend time. questions. So the first and honest question about S4's expressivity is, the last part of the talk is our current best guess. So we'll release blog posts and other things, and I would encourage people to play with them. We have our view of where they're expressive or not. Underneath S4, because they're convolutional, they do run on an FFT or a parallel scan, and we do optimize those, as I mentioned, in the same way that we optimize the flash attention blocks. That's a paper that I think is in a workshop, maybe tomorrow, if I'm correct, from Dan and Herman about how to actually do that optimization. So I think you're seeing a lot of those kind of optimizations. It's clear, by the way, the other piece is there are interesting variants. If you look in the Mamba paper, for example, or even BASE, you can take bits of attention and replace pieces of what we're doing in signal processing and get some benefits. So the trade-offs aren't totally clear. While those models right now are getting past the pure attention baseline, there are hybrids that are exciting. Michael Polly just released something called Striped Hyena, I think last week, that combined attention and these hyena operators and went, had this kind of nice compute optimal properties in some regime. So my point here is not that we know anything, but that there's a whole space of things that you can potentially explore. And so I'm really excited about it. But I don't know any definitive answers.
Great. Please feel free to come up to the mic if someone in your room has a question too. I go up with one more question, which is about how you think foundation models will help us optimize systems. So you could elaborate a bit more on that.
Yeah. Thank you so much for that. Yeah, so one of the projects that we're starting at Stanford is this thing we call SIMS, which is these self-improving models, basically. And the idea here is that there's kind of two obvious places to put foundation models in. There's like the traditional, to me, machine learning for systems where people were replacing heuristics with learned things like learned optimizers and learned pieces. That's really interesting. But there's also this kind of error handling and kind of broader sense in which these foundation models can actually help you in simulation understand what's going on. So I think you're going to start to see some of the foundation models be used for where you would have humans providing impact for the workflow. You're going to start to use it for kind of error checking. You're going to start to use it for a loop where, as we were talking about before the keynote, it may be dangerous to take some of that data and feed it back in. But I think undoubtedly people are going to do that to try and optimize these systems. I mean, one of the things that's just wild to me, if you've had this experience, is setting up software packages that you've never used before, and you go on ChatGPT and it tells you how to do it, and you have this feeling, why am I copy-pasting this thing? Why is it going to optimize more of what I'm doing? Once you start to introduce that into the loop, you have to worry about security and data management and a whole host of other challenges that are present. And I think that's going to be when those systems are able to see the error and fix them, right? It's crazy. It gives you some code, you paste in the error, and it gives you new working code. That interaction is kind of magical. And I think you're going to see that kind of on steroids over the next couple of years. But we're not doing it systematically. Like ChatGPT was a year ago, right? And so most people who were actual users of technology had never heard of it. At the beginning of the year, most of industry was like, what was ChatGPT? It was not in core technical fields like ours. By the end of the year, now everyone's using it and they're expecting it to do things that we don't know if it can do, which is really exciting. I'd rather be in this timeline than any other.
Yeah, great. No, I think, as you mentioned, I think the foundation models, we will use them for the explicit tasks. We just need to figure out which ones to build. Yeah, if there are no more questions, I think we are also almost out of time. So thanks everyone for coming, and thanks again.
Thank you for the amazing talk, very inspiring. I have a question. So you did say they are quite good on images that have sci-fi level. But how about bigger images that you truly need the spatial correlations?
Wonderful.
Do you believe them?
Yeah. One thing here is actually when we were developing them, and if you look in the original papers, we were trying to do two things. We were actually trying to do very high resolution images from medical imaging, exactly as it seems to be in your head. They do seem to be in some ways the only game in town because it was hard to scale up the batch sizes to learn reasonably at that size. So we were very, very excited about those pieces. I don't have numbers that suggest that they're sort of better or worse in the ways I would care about on those medical images, and let me explain that. We did have a bunch of things where we could show that you could learn at lower resolutions and transfer to higher resolutions. Because there's an explicit sampling operator, you can learn at some lower resolution, some higher resolution, and mix them together. You can learn to cross the model things, which seems to give you some benefits. So the absolute quality numbers are better. You'll see that replaced in papers when you start to do the higher resolution images. When I say I don't know if it's in a way that matters to me, we wrote a bunch of work about how, a couple of years ago, about how people, were looking at radiology images and getting fooled by chest drains that were in the test set of the images, and so thought they were doing really well, but hadn't done the rigorous evaluation to say they're actually accurately doing the diagnosis. We haven't really done those studies, and so I don't know, I can't tell you like they're much better, but I'd be delighted to try them out. I don't really see a reason why they wouldn't be better, and this ability to do multi-resolution, I'm super fond of, but maybe, you're always worried when you like an idea too much, so I don't know, how useful it is exactly, but it's a wonderful question, thank you so much.
Thank you.
Thank you for the great talk. I have a question about recurrent networks. LSTM and GRU are popular networks with many years. Right now, S4 comes back. I just wonder whether it solves other problems that LSTM or GRU suffer from, for example, vanishing gradient, slowing gradient, and some exponential decay.
Yeah, wonderful questions. So the stability piece kind of gets you at the exploding gradient question implicitly without having to have any guesswork or heuristics around it. So the signal processing people are good about telling us that sort of things won't explode in kind of machine learning terminology. It doesn't actually do anything about the vanishing gradient problem, and a lot of the work that goes on under the covers has to deal with how the original papers were Elbert figuring out amazing ways to initialize the networks so that they would actually learn in longer sequences. This is not too dissimilar from the kind of folklore practice that's grown up around transformers to get them to train over the last little whiles, but I agree with you that it would be more satisfying if we could say, no, these problems won't happen. So we kind of have a handle on one of those problems, but not the other. The other piece is, I don't know of ways to map the old style of RNNs to the convolutional models, and that was really critical for us to figure out how to train them in bulk. Doesn't mean you can't, because as we showed, they're kind of mathematically identical for this class of models. But that was to me an aha moment where we could now scale them up. Because the other problem with RNNs and LSTMs is they're wonderful models, like use them, train them, 7-8 years ago was a huge proponent of them. The challenge was they were more difficult to scale up because you often would have to do like something like backprop through time, and that was just slower. And so being able to do these in bulk, that link to convolutions, that's what it really uncorked for us. So those were the two things that I would say were practically most relevant to get there. And then, as you said, the other bit we benefited from was, 6 or 7 years of work on making transformer stable, things like layer norms and different training schedules, and a lot of those ended up kind of porting more easily over to S4 because we had been kind of familiar with what problems that they had spiked. So we got to stand on the shoulders of all the great work that made transformers kind of, if you train the first versions, kind of flaky to train, to now where like you press a button and you don't even worry about it. They're relatively simple. So that was the things that I think were different this time from the last time. But yeah, very classical things like the GRUs and the LSTM are huge inspirations and some of my favorite models. It's a wonderful question. Thanks.
Hi there. Hello. Thank you very much. It was very inspiring talk. My question is, what's your take on reinforcement learning? What kind of architecture do you envision for that?
I'm not a reinforcement learning expert, so I will politely comment on it in the way that all professors do, with absolute confidence and no knowledge of the underlying facts. I don't work on reinforcement learning. I've just started working on it recently. I am very excited about reinforcement learning and foundation models because I think there are a bunch of problems where foundation models can provide heuristics for reinforcement learning, but I'm an absolute dilettante at it. I wouldn't even presume to know the beginnings of the right architectures, and I defer to my other colleagues and just follow them and my graduate students. But yeah, thanks so much for the wonderful question.
Sorry, I haven't run a bit time, but really want to answer these questions. So before the state-space model comes, there are a bunch of sparse attention methods, including long form. I wonder what's your opinion on that? As it done?
Yeah, wonderful question. So as I showed in the chart, the long former and the other methods were the things that were on the LRA leaderboard and were the things that S4 actually did this kind of nice leapfrogging for some of those topics. So that was really exciting to watch. They're not dead at all, just as an aside. Those ideas are really powerful and interesting. Actually, I kind of belighted it, but there's a line in my talk that Michael Zhang created a new linear attention. It's a simplified linear attention that's actually part of that based architecture. And I would say that our understanding is there's this kind of interesting connection between linear attention, RNN, and convolutions, kind of this interesting triumvirate. I haven't we haven't really nailed it down yet, but I think we're going to make another try at it. But I think they're all very interesting and related, inspired ideas. They work in different regimes, and I think if you think about them as one architecture to rule them all, I think that's not the way I would view the world, just because I don't think it's a fun way to view the world. But also it hides this thing that in some places linear attention is unbelievable and sparse attention is really unbelievable. And in some places these signal processing methods have something to say. I think there's something deeper going on where they're all kind of, potentially unified, but slight variance on each. So no, we were very inspired, and a lot of those were done by friends. So yeah, I'm very, very excited about all those things. Thanks.
Cool. Thank you everyone for the questions. Let's thank you.